Hello. In this video, we're going to look at directional derivative and gradient. Okay, so to introduce directional derivatives, suppose we have a surface defined by z equals f of xy. Okay, let's draw ourselves a picture. Okay, and then so to go through and introduce the idea of a directional derivative, let's recall the derivatives that we've defined so far with multivariable functions. So we have the partial with respect to x, and that is the derivative in the x direction. And we have the partial with respect to y, and that is the derivative in the y direction. And let's go ahead and put those on here. All right, so let's pick a spot. Let's say we have a point here, and let's say that's point AB. Let's do this. So that's AB. And if we go up, we hit the surface. So that's f of AB. And if we were going to draw the partial with respect to x, what we would do is we would start directly beneath the surface and we would draw a little line segment that's in the x direction. And then you can take that, the ends of that, and extend it up to the surface. Okay, and so the partial with respect to x is the slope of that curve, right, that's directly above the x direction. So it represents the fact that if you're standing on a hillside and you looked in the x direction and you took a step, right, just in the x direction, okay, like if you imagine that there is a grid directly beneath the hill and you have the x direction, so you know that you're walking in the x direction on the hillside, then instead of being a hillside, it just becomes a single curve, and the slope of that curve is going to be the derivative in the x direction. That's the partial with respect to x. Okay, so let's go ahead and do the y next. So it's the same thing, except in the y direction. Okay, so same idea, except this time you're facing in the y direction. You know it's the y direction because if you had a grid directly beneath the hillside, it would be the direction that you walked in or took a step in would be directly in the y direction. So we've got our partial with respect to x is the slope of the curve that you'd get if you just walked in the x direction on the hillside, and the partial with respect to y is the slope of the curve that you'd get if you just walked in the y direction. Okay, now suppose that we wanted to go through and have a direction other than the x direction or the y direction. What if we wanted a derivative in a different direction? Okay, so in order to go through and pick a direction other than x and y, we need to define it in some way. And the way that we can go through and define it is we can use a vector to define it, right? So we're going to go through and say, you know, it's a vector that represents the direction that you would face in on the hillside. So you're standing here on the hillside, and if you're given a vector, that would tell you, a vector in 2 dimensions, a 2-dimensional vector, it would tell you what direction to face in. So let's go through and call that unit vector. So we're going to use a unit vector for reasons that will become clear in a moment. Let's call it unit vector u, and we'll do u1 and u2 for the components. Okay, so what would that look like on our picture? Let's use a different color to differentiate. All right, so the idea is that we would, so you've got the x direction, which is represented by the line that's parallel to the x-axis, and you've got the y direction that's parallel to the y-axis. So what we're going to do is we're going to just draw another direction, something different than those two. And so let's just go through and say, how about here? Okay, so we're going to say that that is the direction u1, u2, right? So you're standing on the hillside, you'd look this way, right? You know, to go through and represent the direction u1, u2. Okay, so here let's put this as direction u equals u1, u2, and that's just, of course, just a arbitrary u1, u2. It could be here or here or here. It could be any number of different directions. We're just putting an arbitrary one. So to go through and figure out what the slope would be in that direction, what we need to do is we need to do something similar to what we did for the x direction and the y direction. We need to take the hillside and take a slice out of it, basically find the curve that you would get if you just looked in the direction of u, having the rest of the hillside kind of drop away. So to go through and represent that, the way that you can do that is we just like we did with x and y, we're just going to extend upward at the ends of that little red line segment to till it hits the curve. So it looks like maybe it would hit the curve, I don't know, maybe here. And it looks like it would hit the curve maybe here. And then we want to draw on top of that. So there's a curve on top of that. Okay, so that's the part of the hillside that we would get if we cut through the object there. Okay, so in order to flesh out, you know, what that slice is going to look like, we do need a little bit more information on how we did x and y, right? So what we did, if you go back to the previous video, is we went through and said the x direction, we said if this is AB, then the point here is going to be a plus h comma b. So that's a step h in the x direction from AB. So you took one h units in the x direction and stepped that amount, okay? And that's what kind of gave us the slice. And you could think of it, there's h negative in the negative direction on the other side. So that's, you've got h in the positive and h in the negative. That's the line segment. And then for y, what we did is we did the same thing, except we stepped h units in the y direction, right? So we're AB, you do h units in the y direction. Okay, and you could have the negative y direction, h units in the negative y direction to have the other side. So you've got h units each way, and that's how you create that slice that you take out of the hillside to take this three-dimensional surface and make it into a two-dimensional surface. Okay, so if we're stepping in the direction u1, u2, then we want to take an h-sized step that way. So what would an h-sized step look like? Well, because of the fact that we defined u as a unit vector, unit vectors are length 1, right? So we would just take one u1, u2 sized step, multiple of h. Anyway, I'll just write it and then it will make more sense. So here we're going to have this point that's at the end will be a plus u1h and b plus u2h. So because u1, u2 is a unit vector, it's length 1. So if you take one h multiple of u1, u2, then that's an h-sized step in the u1, u2 direction. Okay, so you take an h-sized step in the x, an h-sized step in the y, and an h-sized step in the u1, u2 direction, and those are all going to be kind of the corresponding points that we end up getting. Right, so once we go through and we have created our slice, the next thing that we did for the partial with respect to x is we went through and created and just basically took this and turned it into a Calc 1 style limit by saying we've got the limit as h goes to 0 of f of a plus h comma b minus f of ab all over h. Right, and then so for y we did the same thing. This is the partial with respect to x. And then for y, we did the same thing. We went through and turned it into a Calc 1 style limit by, by going through and using these two values and taking the limit as f of a comma b plus h minus f of ab all over h as h goes to 0. And so we just want to go through and just do the exact same thing, except now we're stepping in the u1, u2 direction. So what would that look like? It would look like the limit as h goes to 0. What did you do? You just took this point and plugged it into the function. You took this point and you plugged it into the function. So it makes sense to take this point and plug it into the function. So we're going to have f of a plus u1h comma b plus u2h minus f of a comma b all over h. And so that is going to be the slope that we end up getting in the u1, u2 direction. So what we're going to call that the derivative in the u direction of f. And so this is our limit definition for a derivative in any direction, a directional derivative. Okay, so one neat thing about the directional derivative is that if you were to go through and define the direction for the x direction or the direction for the y direction and use that as your u, then it will go through and it will create the partial with respect to x and the partial with respect to y. So this is kind of cool. I think we've got enough room actually. Well, we'll just do one of the two. We'll just do the partial with respect to x. We definitely have room for that. All right. So what is the x direction represented as a unit vector? Well, as a unit vector for the x direction, actually, let's do this. X direction would be u equals 1, 0, right? And so what that's saying is it's saying that u1 would equal 1 and u2 would equal 0. Take those, pop them in, and so the derivative in the u direction, which is the f direction, x direction in this case, is going to be the limit as h goes to 0. And what do we get? We get f, and we're going to have u1 is 1, so we're going to have a plus h. u2 is 0, so that just kills this whole thing, and we just end up with b minus f of ab all over h. Okay, and so we do end up getting the same result if we go through and apply the directional derivative to either the partial with respect to x, which is just the x direction, or the partial with respect to y. All right, so okay, so that's the neat thing about our directional derivative, is that it is it's backwards compatible. It's compatible with the partial with respect to x and the partial with respect to y. Okay, so there's our definition. Our limit definition. So now how do we go through and convert the limit definition into a definition that is more useful? I mean, you don't want to go through and do the limit definition every single time you want to find a derivative. So how do we convert to a more useful definition? So what we're going to do is we're actually going to make a claim and then go through and see if we can prove that claim. Okay, so that claim, what is that claim going to be? So given z equals f of x, y, and we have a unit vector for the direction, u1, u2, then the claim is going to be that the derivative in the direction of the unit vector for the function f at a comma b is equal to the partial with respect to x at a comma b times u1 plus the partial with respect to y at a comma b times u2. So what is that claim saying? It's suggesting that in order to go through and calculate the derivative in the direction of u1, u2, what we could do is we could go through and we could take some of the partial with respect to x and some of the partial with respect to y and combine them, right? So think of it this way, right? So you're on the hillside and you're facing in the x direction and you get some amount of change. You face in the y direction and you get a different amount of change. And then you face somewhere between the two. And the idea is that you could take the amount of change in the x and the y direction and you could combine it to end up yielding the direction between the two. So that's not an outlandish suggestion that the hillside in the x and the hillside in the y, and then between the two, they're all linked in some way. They're all part of the same system. And so the notion that you could go through and do that is not entirely outlandish, but it does require some proof to go through and prove that actually does work. So let's go through and see if we could do that. First, what we are going to do is we're going to define a function g of h equal to f of a plus h times u1, comma, b plus h times u2. Okay, so keeping in mind that a and b are given and u1 and u2 are given. So that means that for each h input, we would end up producing a number. So this g of h is a function. It does end up producing outputs for each input. Okay, and now separate to that, what we can also do is go through and we can use the definition of the derivative to define g prime of 0 is equal to the limit as h goes to 0 of g of h minus g of 0 over h minus 0. Okay, and so where this comes from is it comes from the very beginning when you first learn about derivatives in Calc 1. If you go all the way back to Calc 1 and you learn about you look at your first derivative form. Your first derivative form would be, if you wanted to go through and find the derivative at a, you take the limit as b goes to a of f of b minus f of a over b minus a, right? So your first form for the derivative was in the form of a slope, right? You had change in y, change in x, and then you took the limit as one point went to the other, right? As b goes to a or a goes to b, doesn't really matter. If you had a going to b, then this would be f prime of b. And so that's your initial form that you looked at before we created the limit, the limit definition with the a plus h minus f of a over h. That's the second derivative form that you encounter. So you've got to go back to the limit, the initial limit definition of the derivative, and you end up getting this format. And so what you can see here is that this format and this format matches. We just have replaced the g's, replaced the f with g. We've replaced a with 0, and we've replaced b with h. And so it's all the same stuff. And so just this is a consequence of the definition of the derivative, is that we could go through and find g prime of 0, and it would equal the limit as h goes to 0 of this. And then so from there, we could go through and actually take our definition we have above, and you could actually pop it in there, right? So that would get you to the limit as h goes to 0, and we'd have f of a plus hu1 comma b plus hu2 minus f of a comma b all over h. Okay, so yeah, so if you plug in 0 for h here, what happens? It kills the hu1, kills the hu2, and you just get f of ab. That's the second piece here. So g of 0 does give us f of ab. G of h, clearly just substituting that in there. And then so this tells us that g prime of 0 equals this, which is, right, that's our definition. That's our definition for the derivative in the u direction for f. Right, and so that would be at AB. Okay, so we're halfway there. The second part of the proof is that we need to go through and define g of h using a composition of functions. So let's say we also go through and say, let g of h, this is separate, separate from the steps that we just did, let g of h equal f of x comma y, where x equals a plus h u1 and y equals b plus h u2. Okay, and so this is still a single variable function, and that if you took x and y, plugged them in, what would happen? We would get g of h equals f of a plus h u1 comma b plus h u2. And so g of h is still a function of h because a, b, u1, and u2 are all given. Those are all numbers. So the only variable here that could potentially be changing would be the h. Okay, so this g of h is still a function of h. All right, so that's just kind of an aside, just to go through that. If we have g of h on this side, f of x, y on this side, it maybe doesn't look like it's a function of h, but it's because the h is in the x and the y. Okay. So the next thing we're going to do, we're going to go through and we're going to take this. So that was just a check. So we're going to go through and differentiate both sides. So we're going to get g prime of h. So we're differentiating with respect to h. Since h is the independent variable here, if we differentiate, we're differentiating with respect to h. So we're going to have the derivative with respect to h of f of x comma y, right? So we differentiate both sides. And if you do that, we need to go through and differentiate f of x comma y, since it's a composition of functions, right? So we've got the outer function f of x, y, and then inner function a plus hu1, b plus hu2. We need to go through and use the chain rule to figure out what the derivative would be. So if you watch the previous video, the chain rule tells us, so we can start with, if we start with f is in terms of x, and it's in terms of y, and then x is in terms of h, and y is in terms of h. So to go through and calculate the derivative when you have a composition of functions like this, we can use a derivative tree. And so you get the partial of f with respect to x, you get the partial of f with respect to y, you get the derivative of x with respect to h, the derivative of y with respect to h. And so taking all that and putting it all together, what happens? We get g prime of h equals the partial of f with respect to x times dx dh plus the partial of f with respect to y times dy dh. Okay. And now if you take a look, what are these things? All right, so the partial of f with respect to x, that is going to be, we're just changing formats here. That's going to be the f of the sub x. And then what is the derivative of x with respect to h? Well, here's the derivative. Here's x. If we differentiated this with respect to h, what would we get? Well, the derivative of a with respect to h would be 0, and the derivative of hu1 with respect to h would just be u1. So we're going to end up with u1. And then over here, we're going to have the partial of f with respect to y. So we'll just change formats here. And then the derivative of y with respect to h, we get u2. Okay, so the only thing that's a little goofy here is because I'm using shorthand, we actually need, if we write out what the partial with respect to x is, we're going to have x comma y in here, right? Because we're still this is still our definition, times u1 plus partial with respect to y at x comma y times u2. Right now, where x is a plus hu1 and y is b plus hu2. So we still have our composition here. Now, the trick, though, is that if we go through and plug in g prime of 0, right, what's going to happen? Then the x, if you go ahead and look at the x, if h is 0 in there, then x becomes a. So we're going to have a, and then if you plug in 0 for h, then y becomes b, u1 plus the partial with respect to y, and then the same thing here, times u2. Okay, so at this point, we could see that g of h is defined to be equal to f of x, y, and g of h, if you go through and plug the composition in, it's equal to f of a plus h u1, b plus h u2. So g of h equals this function. G of h, same function, same definition. So this is the same g here that we have here, and the same g here as we have here. So if you have g prime of 0 equals the derivative in the u direction of f of a b, and g prime of 0 equals the partial with respect to x at a b u1 plus partial with respect to y at a b u2, then that means you could go through and set those two equal. And by setting g prime of zeros, setting g prime of 0 equal, we get that the derivative in the u direction of f of a b equals the partial with respect to x at a b u1 plus the partial with respect to y at a b u2. Okay, right? So g prime of 0, partial derivative, directional derivative, g prime of 0, the definition that we want, and so we're good. We're done. All right, so that's the proof. All right, so just to recap the structure of the proof. So our goal was to prove that the derivative in the u direction of f of ab equals this. And the way that we did it is we went through and defined g of h, used the definition of the derivative to create this, and then manipulated it until we had the limit definition from the directional derivative. So we need to go through and prove that the derivative in the u direction of f of ab equals this. We need to have the limit definition in there somewhere, okay? Because that's what we're shifting from, right? So how do we convert the limit definition to a definition more conducive to calculation? Well, we need to have the limit definition in there. So part A, if you want to think of it in two parts, part A is all about going through and linking the limit definition to something, right? We linked it to this thing g prime of 0. So that was the goal of part A. And then the goal of part B is to go through and take that same something and link that to the result that we want. And once you've got one side linked to the limit definition and the other side linked to the result that you want, then that basically makes it so that you've linked the limit definition to the result you want. And then that's what we did, and that's the end. So that's the proof. Now, one thing you'll notice, we went through and proved it in the case of AB where we had a specific point. We can always go through and make this more general, just to say, hey, you know, we let A equal X and let B equal Y. We haven't chosen what the point is. You can just make A and B generic. And so this can be extended to the derivative in the u direction of f of xy equals the partial with respect to x of xy u1 plus partial with respect to y xy u2. Okay, so all of this can be made generic, where instead of plugging in the point before you go through and do the calculations, here you're just plugging in the point after you do the calculations. Okay, so with all of that done, we have defined what the directional derivative is. It is the slope of the tangent line in the direction of the unit vector u1, u2. We have gone through and linked that definition to the partial with respect to x and partial with respect to y, so you can see the similarity between them. Then we've gone through and taken that limit definition and manipulated it and proven that it can be rewritten into a form that's more conducive to calculation. And so what's left is to go through and actually do calculations with it. So let's do that now. All right, so we've got a function. And we've got a point. And we've got a unit vector. And so it wants us to go through and find the derivative, the directional derivative for the function f of xy at the point -1, 3 in the direction 1 over root 5, 2 over root 5. So to do that, right, if you go back to our definition, here's our definition. What do you need? You need to have partials, and you need to have the point plugged in. So we go through and find the partial with respect to x. So that's going to be 2x. We find the partial with respect to y. That's going to be 6y. You can then take the point and plug it in. We get the partial with respect to x at -1, 3. And that's going to be -2. We find the partial with respect to y at -1, 3. and that's going to be 12. And then the derivative in the u direction of f of x, f of negative 1, 3, is going to equal the partial with respect to x at negative 1, 3, which is negative 2, times u1 from the unit vector, which is 1 over root 5, plus the partial with respect to y at negative 1, 3, that's 12, times u2, that's 2 over root 5. And so we get negative 2 over root 5 plus 24 over root 5, which equals 22 over root 5. And that's it. That's the derivative. So, and to interpret this, this is the slope in the direction of the unit vector. Okay, so if you're standing on the hillside and you face in the direction u, then the derivative is 22 over root 5. All right, let's try another one. Okay, so the thing about some of these problems that you may encounter if you go through and do problem sets in textbooks is that they may not always give you a unit vector. They may just give you a direction vector. And if that happens, you need to go through and normalize the unit vector or normalize the vector to make it into a unit vector. So we'll say vector w is going to equal negative 1, 1. And then to normalize it, you divide by the length, which is the square root of the component squared. The square root of negative 1 squared is going to be 1 plus 1. And so, negative 1 squared is 1. 1 squared is positive 1. And so we get the square root of the sum of the components squared. And so that is converted into negative 1 over root 2, comma 1 over root 2. Okay, and then so next you can go through differentiate with respect to x, and you'll get natural log y. Differentiate with respect to y, and you'll get x over y. The derivative with respect to x at the point 2 comma e, so you'd be plugging in e, so natural log of e is going to be 1. And the partial with respect to y at 2 comma e is going to equal 2 over e. And now combining those with our unit vector, we get the derivative in the direction u of f at 2 comma e is going to equal the partial with respect to x, which is 1, times u1 from, or w1 in this case, from our unit vector. Oh, hold on, not a comma. Plus the derivative in the y direction, which is 2 over e, times u2, or w2, which is 1 over root 2. And we get negative 1 over root 2 plus 2 over e root 2. So if you multiply by e over e here, you'll get negative e plus 2 over e root 2. And so that's, if you plug in 2.71 and change for e, you could simplify this into a numerical value for the slope. So that's would be if you're standing on the hillside for x natural log y at point 2 comma e, and you're facing in the negative 1, 1 direction, then this is the slope that you'd end up getting when you go through and calculate the directional derivative. Okay, so what's next? let's look at the gradient. All right, so what is the gradient? All right, so let's go through and figure that out. Given z equals f of xy, given a generic unit vector, so this could be any vector, any direction. This is a unit vector, but it's not specific. It's just a generic one. So this is basically could be any direction. If you were again kind of standing on the hillside, it could be any direction. Put that together. If we go through and look at our derivative of f in the u direction, and again u being completely generic, we get the partial with respect to x u1 plus the partial with respect to y u2. So that's just the definition we were just using to calculate the derivative. Now, if you'll notice, this could be the result of going through and calculating a dot product where we have the partial with respect to x, partial with respect to y, dotted with u1 comma u2. Right? If you go back to dot product, you multiply component wise and then add. So we get f of x partial with respect to x u1, partial with respect to y u2, and then you just add the two. So we could simplify this into the dot product. And now, again, this is ancient history at this point, if you're actually taking this course. But the dot product, we have an alternate definition for the dot product, where you have, if we have a dot b equals length a, length b cosine theta. So we're going to go through and convert from the left side over to the right side. So if we have the right side, we'd have the length of the partial with respect to x, partial with respect to y, dotted with the length u1, u2 times cosine theta, where theta is the angle between these two vectors, right? Theta is the angle between a and b. All right, that doesn't matter just yet, but it will. Okay, so this, we don't know what the partials are, so we're just going to leave that alone. That doesn't change. And then what's the length of u1, u2? Well, we said that u is a unit vector, so the length of u1, u2 is going to be 1. So we're going to get 1 times cosine theta. And so this is the length of the partial with respect to x comma partial with respect to y vector times cosine theta. Now, again, I've said it a couple times because it's really critical to understanding what's going on here, and that is that u is unspecified. So u could be anything, any vector we wanted. If you go through and pick any u, any generic u, pick multiple u's, no matter what u you pick, you're going to end up getting this result where you're going to have the length of this thing times cosine theta, where theta is the angle between these two vectors. So because of that, because u is generic, this is giving us every possible outcome that we could get from the directional derivative. All right, so if we have every possible outcome here, then what we could do is we could go through and think about what those results would look like, right? So what are the possible results that we could get? If you went through and played around with the right-hand side of this, can you go through and discover anything? Okay. Well, think about it for a second, pause the video maybe, and see if you could discover anything. All right, so the thing that you could discover here is that cosine theta is bounded. Cosine theta is less than or equal to 1. The maximum value that cosine theta can take on is 1, right? So thus, the max value, the max directional derivative is the length of this vector. Okay. So this basically gives us a maximum directional derivative. And so if you think about what the directional derivative is, it's just the derivative in a direction. So it really gives us the maximum derivative. And what is the derivative? It's the slope. So it gives us the max slope. So if you're thinking about, so you're thinking you're standing on that hillside, you know, that I keep using as an example. If you were asked what's the steepest the hillside could possibly be, this we can just go through and just take the function, whatever the function is, just pop it into this calculation, and boom, the answer just pops right out. Pretty amazing result. Actually, it's kind of neat. The notion that you could go through and just by taking the directional derivative and using the formula and turning it into the dot product and simplifying the dot product, you can go through and you can show that the maximum value the directional derivative can take on is the length of this vector, this thing, okay? And you know, and so that's going to be our max slope. So what else can we go through and say about these results? So when does so the max result is this, so when does that happen? Right, it happens when cosine theta equals 1. Right, and when does cosine theta equal 1? That occurs when theta equals 0. What is theta? Theta is the angle between the unit vector, right, the direction vector. It's the angle between the direction vector and this vector. Right, so what that's saying is that this maximum value that we just got by just going through and manipulating it, it occurs when, hold on. It occurs when u equals this vector. So where's that coming from? Let me just recap that, because that may be a little bit of a jump there. Right, so we went through and manipulated this, got to the directional derivative equals the length of this guy, cosine theta. We discussed that cosine theta is bounded. The maximum value it can take on is 1. Thus, the maximum value of the directional derivative is the length of this. Okay. Then the next question is, when does that maximum value happen? When does this equal the length of that? And that's going to happen when cosine theta equals 1. So it happens when cosine theta equals 1. And then when does cosine theta equal 1? It happens when theta equals 0, right? And then what is theta? Theta is the angle between these two vectors. If the angle between these two vectors is 0, then it's saying that these vectors point in the same direction. Okay, and since u1, u2, the direction is not specified, it's just completely generic, then that tells us that it occurs when u equals this guy, which would be specific, right? If you had a problem, you'd go through and you'd calculate the derivatives with respect to x, and you calculate the derivatives with respect to y. So we'd actually know quantities here, whereas this guy is generic. It could be any direction. Okay, so it occurs when u equals this, right? So not only do we know what the maximum slope is, not only do we know the maximum derivative, it occurs here. We also know the direction in which it happens, and it happens in, you know, the direction of this without the lengths. So this is the direction of the max derivative. Okay, and so you'll notice here that we've got the length of this this thing, we've got, that's the direction of that, that ends up occurring when we're in the direction of that thing. Well, this thing, is important enough, the fact that it came up multiple times here, it comes up in other contexts too. That thing is what we define to be the gradient. That's the name we give to it. So the thing that you need to know about the gradient is that it's a vector, and its qualities that it has, so our characteristics, there are two important characteristics. One, it gives the direction of maximum change, direction of maximum derivative. Which is interpreted to be the direction of maximum change. Usually the second of those two is the one that is quoted. Direction of maximum change rather than direction of maximum derivative, but those are the same idea. Okay, so that's a pretty amazing result. Okay, so think again, back, you're standing on the hillside and someone asks you, which way is steepest? And you could just go through and you can just take some partial derivatives and immediately that direction just pops out. That's incredible. And then second, the maximum change is the length of the gradient. Okay, so both of those results came out of the steps that we just went through here. Here's the first one. We found the max first. We did the max first, and then after we found the max, we went through and showed that that max occurs when you're facing in the direction of the length of, or sorry, when you're facing the direction of the vector that has partial with respect to x and partial with respect to y as the components, which is what we have here. Yeah, I mean, I'm kind of bouncing back and forth with the notations, but this is the same as that. Okay, so there's our gradient. That's where it comes from. That's the proof / explanation for for where that result comes from. So what's left? To go through and practice using it. All right, so find the maximum change and the direction in which it occurs. All right, so we've got f of x comma y, so we've got our surface here, and it's 3x squared y plus 2y squared. And we've got a point where they want us to go through and find this. 1, 2. All right, so and so just to stick with our analogy, so here's our function that defines the hillside, and then here's the point that you're standing on the hillside. And you're being asked, what's the steepest slope that you could get if you went through and just calculated all of them at that point? What's the steepest one? Okay, what's the maximum change? Right, so to go through and find that, we can go through and we can use our result. The maximum change is going to be the length of the gradient. So first we have to find the gradient. So the gradient vector is going to be equals, you want to take the derivative with respect to x. So we're going to get 6xy and then the derivative with respect to y. So we're going to have 3y squared. Oh, hold on. 3x squared plus 4y j. So this gives us a generic gradient that we can use at any point. And then if we want to calculate the gradient specifically at 1, 2, we end up getting 6 times 1 times 2. So we're going to get 12i. And then plus 3 plus 8. So we're going to have 11j. And the length of we want to ask for the maximum change. So the length of the gradient is going to be the square root of 144 plus 121 equals the square root of 265. So this is the max change. Right, this would be, again, you're standing on that hillside, you go through and you calculate all of the slopes. This one will be the biggest one. Right? So there's an infinite number of possible slopes. You've calculated all of them, and we can go through and figure out what the biggest one is. That's such a cool result that you can do that. All right, that's the first part. Find the max change. We've done that. And then find the direction in which it occurs. And in order to find the max change, you have to go through and calculate the gradient, and the gradient is the direction. So that's this guy right here. So this is the direction of max change. So not only can we figure out, you calculate all the derivatives, you can figure out which one's biggest. This can tell you what's the direction of it. This tells you which way to face to go through and get that result. Possibly the coolest, most interesting result in all of multivariable calculus. I don't know, possibly. It's one of my favorites. Okay, let's go through and try another one. I think we've got enough space down here. So we've got f of x comma y. And we've got x e to the y. And then let's say our point is going to be -3 natural log 2. So we've got our hillside, we've got our place where we're standing, and you're asked what's the steepest slope you could get and what's the direction for that steepest slope. All right, in order to figure that out, we need the gradient. Take the derivative with respect to x, you get e to the y. Take the derivative with respect to y, you're going to get x e to the y j. Plug in the point. We got the partial with respect to x at -3 ln 2. So if you plug in ln 2, we're going to get e to the ln 2, so that's just 2. And then over here, we'll have -3 times e to the ln 2, so that's going to be -6. Okay, and then the max change is the length of the gradient, so we get the length of 2i minus 6j. And so what that's going to be? That's going to be the square root of 4 plus 36. So we get square root 40. So that's the steepest slope. That's the max change. And then the direction in which it occurs is the gradient itself without the length. So here's the direction of max change. Okay, so that's all there is to it. Now that's not the end of all of the things that the gradient is useful for. Let's talk about gradients and level curves. All right, so let's suppose that we have z equals f of xy. So we've got a function. And we go through and find a level curve. Okay, so if we go through and put those together, we get some level curve. And let's say we'll just go through and draw it. So let's say that's our level curve, right? So this is k equals f of x comma y. All right. So in that case, the gradient, so this is a statement that we will go through and prove. The gradient is orthogonal to the level curve for all of the points that are on the level curve. So that's another way of saying, so if you just pick some point that's here on the level curve, right? So orthogonal to the level curve, so 90-degree angle, we could go through and draw a vector. That vector is going to be the gradient. The arrow's really big. I'm not going to do that for every single one, but you get the idea. So that's gradient of f, gradient of f. So orthogonal to the level curve is going to be gradient of f. So there's a couple things that are kind of neat about that, right? So it tells you the direction that you would head in if you were standing on the level curve that would have max change, right? So think about it. So if you're standing at this point on the level curve, you know that if you rotate, if you go 90 degrees from the level curve, that's going to be the direction of max change. So that's kind of a neat result that if the level curve represents all the places that are at the same height, right? If you think of the level curve like it's a topographical map, and this is a mountain that you're that you're climbing, you're walking on, and this line represents all of the places on the mountain that are at the same height, that are 1,000 feet, for example. And if you're standing here and this is 1,000 feet, and this is the direction to stay at 1,000 feet is this way, rotating 90 degrees from staying at the same height would give you the direction to climb as rapidly as possible. That's cool. That's a cool result. That's really interesting. That might be something that you'd guess that it could work that way, but actually being able to have some evidence that it works that way, that if one direction is flat, then 90 degrees from that direction is the steepest climb. That's pretty neat. All right, so let's see if we can go through and prove this, right? Because it's a nice result, but if it's not true, then it's useless. So what we can do is we can go through and define k equals f of xy. So what is that? That's this curve. We can go through and define that parametrically. All right, so the way that we end up doing that is we're going to say let x equal x of t, y equal y of t, and we'll just leave these completely generic. So we're saying we figure out, you have to define this however you have to, so that you end up getting this this curve, the curve that represents the same curve as k equals f of xy. Now, effectively, this means that we also have gone through and defined a vector function, r of t, that if you plug in t values will end up yielding vectors whose termination points are all on this curve. Okay. Now, so the next result from that, because of that, if we have a vector function that yields all these results, we could go through and take the derivative of that vector function, and then r prime of t, right, would give us tangent vectors. Okay, so that means that we could go through on here, and we know that there are tangent vectors. Now we know this, so we're still trying to prove the gradient factor, but we don't need to prove anything. This is already proven that if you can go through and you've got a curve, you can always take a curve that's defined, and you can always define it parametrically. If you define it parametrically, you can always convert the parametric form into the vector form, and then if you take the vector form and differentiate it, you get tangent vectors. End of story. So if we've got a curve, we've got the parametric representation, and we've got tangent vectors. Okay, so now the question is the gradient orthogonal to those tangent vectors, right? Is there a 90-degree angle here between these two? Can we go through and show that in some fashion? Well, yes, you can. All right, so if we've got k equals f of xy, we know this is true. And specifically, we know it's true for any xy that lies on the curve. So what you can do is you can actually take your parametric definition, which defines the points that are on the curve, and you can actually plug it in, and you know this will be true. So this is technically not true for any xy, but it's true for xy that lie on this curve. And what are the xy that lie on this curve? They're the xy that are produced by our parametric definition that we just created. So you can go through and replace xy with our parametric definition. And so we know that this is going to produce k outputs when we plug in x of t and y of t for x and y, since those are points that are on the curve. Okay, so the next thing you do is you go through and differentiate with respect to t on both sides. The derivative of k is just a constant, so we get 0. And then on the right side here, if we're trying to differentiate a function that's defined in terms of two different components, and each of those components is defined in terms of a third variable, then there's our chain rule derivative. Again, second time in one video. So if you've got f is defined in terms of x and y are defined in terms of t. And so you've got partial of f with respect to x, partial of f with respect to y. It's not coincidence that we went through and did the chain rule right before we did this section. And then the derivative of y with respect to t. And so you multiply down the chain and add. So we're going to get the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. And if you take a look at this, what is that? It's the result of a dot product where you'd have, I'm going to change notations here to the subscript. Partial of f with respect to x, there you go. Partial of f with respect to y, there you go. And what is it dotted with? It's dotted with dx dt and dy dt. So close to running out of space here. And so what is that? That is the gradient dotted with, and then what is this? It's the derivative of our parametric equation. Well, if you write out what r of t is, it's x of t comma y of t. And then so if you differentiate that to find r prime, which is our tangent vector, then you get the derivative of x with respect to t is dx dt, and the derivative of y with respect to t is dy dt. So this is r prime. It's the derivative of this. It's the tangent vector. So what does this prove? It proves that the gradient is orthogonal. Oh, why is it prove that? It's because our result is 0. If you have a lot of pieces being pulled together from throughout the multivariable calculus course. We have the dot product of two vectors equal to 0. That tells us that those two vectors are orthogonal. So this result here tells us that the gradient of f is orthogonal to r prime of t, and r prime of t is the direction of the curve, the direction that the curve is heading in. So that tells us that the gradient is orthogonal to the curve. Cool result. Another cool result. One way that you could, interesting way that you could go through and use this is if you had a series of level curves. This is kind of neat. Let's jam it into this same page. You've got a series of level curves. So here's level curve, and then here's another level curve, and then here's another level curve. If you start here, you're standing there. If you calculate the gradient, it will tell you the direction to climb as quickly as possible. Yeah, this is actually not going to work. Let's put a second peek. It'll tell you the direction to climb. So you go there, and then you recalibrate there, and it tells you the direction to climb. And you can actually go through and recalibrate your way so that you could climb the mountain as quickly as possible by using gradients. All right. Is that it? No, that's not it. That's not the end of the cool things that you can do with gradients. It's kind of a never-ending story of cool gradient stuff. What about gradients and level surfaces? All right, so let's suppose that we have a surface given W equals f of x, y, z. Oh, sorry, let's say we have a level surface. So we've got a three-dimensional function, that's three input function, which if you were to try and visualize this is in 4 dimensions. So we can't visualize it, but we can go through and visualize level surfaces for it by, picking specific outputs. So we can go through and say, let f of x, y, z equal k be a level surface. So this is the set of points for x, y, z such that we get an output k. And that is something that we can go through and visualize, because that's going to be a surface that's in 3 dimensions. So what does that look like? So let's say we have a surface. And that surface is k equals f of x, y, z. All right, so just taking our previous result, we can take our previous result and you can extend it, right? If you're skeptical that this result could be extended to level surfaces, everything on this page you could go through and reinterpret as a surface instead of as a curve, and everything still holds up. So there's nothing here that cannot be extended by just adding another input to the function. And so because of that, we can go through and we could say, if we have a level surface and we go through and calculate the gradient, then the gradient would be orthogonal to the level surface, just like the gradient was orthogonal to the level curve. So if the gradient is orthogonal, that means if you just pick some point here on our surface, we could go through and calculate the gradient of f would end up pointing orthogonal to the surface. So, if the gradient is pointing orthogonal to the surface, what could we use that for? When have we wanted to go through and find a vector that pointed orthogonal to a surface? Well, if you think about it, that's exactly what we were trying to go through and do when we were defining tangent planes just a few sections ago. So if you go through and put a tangent plane here around our point, okay, then this vector, the gradient vector, ends up being orthogonal to the surface. If it's orthogonal to the surface, it's also going to be orthogonal to the tangent plane. Okay, so thus the gradient of f produces the normal vector to the surface. So, and that's just taking our previous result for the gradient and level curves and just extending it to level surfaces. So no proof is necessary. We've already proven it on that previous page. All right, so if the gradient of f is the normal vector to the surface, that means we could use the gradient of f to go through and find the equation of the tangent plane. All right, so this is going to turn into an alternate formula for the equation of the tangent plane. All right, so thus gradient of f, which equals partial with respect to x, partial with respect to y, partial with respect to z, is the normal vector for the tangent plane at point x, y, z. And thus, we can go through an alternate equation for the tangent plane. Actually, let's hold on. I should do something else. Not x, y, z. Let's go through and put x naught, y naught, z naught. Usually, if you just use x, y, z, it's implied that those are generic, where we mean a specific point as the normal vector for the tangent plane at a specific point, x naught, y naught, z naught. So that's an alternate equation for the tangent plane. Is partial with respect to x, x naught, y naught, z naught, times x minus x naught, plus partial with respect to y, x naught, y naught, z naught, y minus y naught, plus partial with respect to z, x naught, y naught, z naught, times z minus z naught equals 0. So that is not the same definition as we had previously given for the tangent plane. So I do want to be clear, this is a different definition. So there's two different definitions for going through and finding the equation of a tangent plane. This is an alternate equation. This equation tends to be more flexible. And so in that way, it tends to be a better definition because of the fact that it can handle surfaces that are not defined explicitly. So if you go back and watch the tangent plane video, in the tangent plane video, it's assumed that the surface is defined explicitly, right? It's assumed that you have a surface z equals f of x, y. Well, what if you don't have a surface that's defined explicitly and you still want to go through and find the equation of the tangent plane? That formula from that previous video is useless. You need to have the plane defined, or you need to have the surface defined explicitly in order to go through and use that tangent plane definition. This definition does not require that. So it's a more powerful, more flexible definition for finding the tangent plane. And it still can be used on explicit functions as well. So it's just an all-around better definition. Okay, so the key to being able to go through and use this tangent plane definition is that you do need to know what f is. All right, so the key is that you have to have the function f. It has to be in terms of all three variables that are all on one side, and you have k, you have to have a number on the other side. So it's got to be in the form of a level surface of a function that's in terms of three variables. Okay, so three variables, one side, number on the other. Those three variables are the function. Three variables on one side, number on the other. Those three variables are the function. So this is f of x, y, z. And in this case, 4 is k. Does that make sense? Does that see that? You've got 4 here, and then f of x, y, z over there. 4 here, f of x, y, z. All right, so once, assuming you've defined f properly, from there, it's just partial derivatives and plugging in points. Okay, so partial with respect to x is going to be 2x. Partial with respect to y, 2y. Partial with respect to z, 2z. Find the partial with respect to x at negative 1, 1, root 2. That's going to be negative 2. Partial with respect to y at negative 1, 1, root 2. That's going to be 2. And partial with respect to z, negative 1, 1, root 2 is going to be 2, root 2. And then so our tangent plane is going to be negative 2 times x plus 1 plus 2 times y minus 1 plus 2 root 2 times z minus root 2 equals 0. Okay, and so we were able to go through and find the equation of the tangent plane for a function that was not defined explicitly, right? Again, notice not defined explicitly. Z was not by itself. We did not have z equals f of x, y. And so we were able to still go through and find the equation of the tangent plane. If you were using that other format, then you'd have to go through and solve for z, get z by itself. You have to go through and do a square root. The square root would have a plus or minus. You'd have to look at the point and figure out, do I use the plus or do I use the minus? So you've got to jump through a bunch of hoops. None of those hoops are necessary if you use the gradient version of the tangent plane definition. Now, so one more thing. Let me go through and show you how you could use this gradient version if you did have a function that was defined explicitly to find the tangent plane. So let's say we're asked to go through and find the tangent plane, and they give us z equals x squared y minus 3xy squared. And they go through and they tell you they want you to find it at 1, 1, negative 2. All right, so you're asked to go through and find the tangent plane. And so for this one, assuming you had the equation memorized, the formula memorized, you could just go through and use that definition from the previous video. However, let's say that you really love this new definition because you think gradients are cool, and you really want to use it. All right, so if you're going to use it, then what does it have to be? It has to be in the form of a level surface. So you have to have x, y, and z on one side and a number on the other. Okay, that's the requirement. So how do we do that? Well, you got to have x, y, and z together on one side. So you got to move the z over. And if you do that, you'll get 0 equals x squared y minus 3xy squared minus z. And now notice you've got x, y, and z all together on one side equal to 0. So 0 would be the k, and this is the f of x, y, z. And then from there, once you've done that, it's all just partial derivatives and plugging in numbers. So you can do partial with respect to x, and that's going to be 2xy minus 3y squared. Partial with respect to y, we're going to get x squared minus 6xy. And then partial with respect to z is going to equal negative 1. And plug in the point, partial with respect to x at 1, 1, root negative 2. So if we plug in 1 for x and 1 for y, what are we going to get? So this is going to be 2 minus 3, that's negative 1. And partial with respect to y, plug in the point, so that's going to be 1, 1, negative 2. And that's going to produce 1 minus 6, so that's negative 5. And then partial with respect to z at the point is still going to equal negative 1 because it always equals negative 1. Okay, and so take those and just plug them in. So we're going to have -1 times x minus 1. And then -5 times y minus 1. And then -1 times z plus 2 equals 0. Okay, hold on. I'm just checking my work because in my notes I put -4 here. That doesn't, -4 does not look right. It looks like it's correct. Differentiate with respect to y. We get x squared minus 6xy. Plug in 1 and 1. You're going to get 1 squared is 1 minus 6 times 1 times 1. Yep, -5 is right. Oh, my notes are wrong. Okay, so that's it. That's all the cool stuff for gradient for today. Thank you for watching. See you next time.